So we'll continue with the next series of transition elements, the important question and answers. Let's go on. See the first question on the screen here. The transition elements display a variety of oxidation states. Why it is so? It is because of partially filled d orbitals. That is due to participation of n-1 electrons in addition to ns electrons. Okay. The next question. Write the highest oxidation state of an element with atomic number 23. So can you just recollect what is that? So it is related to the first transition series. Okay. First transition series starts from scandium. Scandium, that is atomic number 21. Scandium followed by titanium, then is vanadium. So atomic number 23 stands for vanadium. Now what is the configuration of vanadium then? We know it is a transition element, and transition element always has the electrons in d orbitals. Accordingly, argon with an 18 electron series followed by 4s, 2 and d3, 3d3, right? So accordingly we can find out the highest oxidation state is 5, because in case of d orbital series, the s electrons as well as n-1 d orbital wale electrons have an participation with reference to the oxidation state. So 3 plus 2 makes 5. The next question on the screen. Explain why scandium 3 plus is more stable than scandium 2 plus. See, as far as scandium 2 plus is concerned, it does not exist, because the energy which is available in such reactions is rather more sufficient to remove 3 electrons, and accordingly it can easily form scandium in its plus 3 state. Okay. Moreover, if you look at the electronic configuration of scandium, you can find out when 3 electrons are lost, it will achieve a D0 configuration. So it's a highly stable configuration, and as a result, scandium 3 plus would be more stable than that of scandium 2 plus, right? Move on the next question now. Why does manganese ion in its 2 oxidation state show maximum paramagnetism among the bivalent ions of first transition series? I hope the question is clear. So the reason for this is because it has maximum number of unpaired electrons in 3d orbitals. If you again check out for the manganese 2 plus in its 2 plus form, it will have a 3d5 electronic configuration. So it has a maximum number of electrons. As a result, we can say it shows maximum paramagnetism. Okay. We'll move on the next screen now. Check out the first question there. The magnetic moment of transition metal is found to be 3.87 Bohrs magneton. Calculate the number of unpaired electrons present in it. So it is, see, unpaired electrons could be calculated for the transition metal series, particularly for the first transition series. It is calculated as mu is equal to root of n plus 2. So accordingly, they have already given you mu is 3.87. So that would be 3.87 is equal to root of n plus 2. Taking square on both sides and further solving for n, you'd get n is equal to 3. So what are the number of unpaired electrons in this case? It's 3. Okay. Move on the next question. Name 3 such elements which are non-transition elements but belong to D block of the periodic table. So these are the last elements of the transition series, the first, second and the third transition series. So which are those 3 elements? Zinc, cadmium and mercury. Okay. Right. Check out the next question now. The transition elements have colored ions. Why? See, in this case, the coloration is due to DD transitions. So one electron from the d orbitals could be excited to another within the same shell. Okay, and some frequency from the visible light is absorbed during this transition and its complementary color is exhibited. Okay, so the main reason behind coloration is the unpaired electrons which are present and the DD transitions which could take place and the corresponding complementary color which you can observe. The next question now. Why cadmium 2 plus salts are white? So whenever a particular ion is been said that it is white, that means that the probably the DD transitions are not possible in that case. Okay, even in this case, copper, if you go for this cadmium 2 plus salts, you can find it out that its electronic configuration comes to 4d10, and accordingly DD transitions are not possible because it is a highly stable configuration. They have fully filled d orbitals, so no DD transitions, and as a result no coloration. So cadmium salts are white in their 2 plus state. Check out the last question on the screen there. Why are the most of transition metals hard? So what could be the reason for this? See, the metallic bonds in most of the transition metals are quite strong, and this is due to the greater effective nuclear charge and the large number of valence electrons, right? And due to the presence of such strong metallic bonds, we could say the transition metals are hard. Let us see the other questions now. The next question, why zinc 2 plus salts are white while nickel 2 plus salts are blue? Again, you can relate it with the help of electronic configuration. Zinc in its 2 plus state has completely filled d orbitals in the form of 3d10, while nickel 2 plus has incompletely filled 3 orbitals, that is 3d8. So in case of nickel 2 plus, you can say there are DD transitions which are possible, giving the coloration blue in that case, the complementary color visible in the visible range. So it results in blue, whereby in case of zinc 2 plus, they have fully filled d orbitals and no DD transition, no coloration. The next question. Most of the transition metals do not displace hydrogen from dilute acids. Why? See, this particular question could be answered with the help of the reduction potential values. So it has been observed that most of the transition metals have positive reduction potentials, and accordingly they cannot displace hydrogen from dilute acids easily. Okay. The next one. What is the highest oxidation state shown by any transition metal? So the highest oxidation state is not shown particularly by the first transition series elements. However, it is possible in case of second and third transition series, and that oxidation state is +8. Okay, and it belongs to ruthenium and osmium. So there are certain complexes of ruthenium and osmium whereby the oxidation state is even high, as high up to +8. So that is the highest one. The next one. Transition elements form many alloys. Why? So it is due to the similar atomic sizes of transition metals which can easily replace one another in the crystal lattice, right? Resulting in solid solutions. And that is, solid solutions is nothing but the alloys. Should I repeat it again? So why this transition elements form alloys? The main reason behind that is it has similar atomic sizes. Okay, the transition metals are almost having similar atomic sizes, so they could easily replace one another within the crystal and results in the formation of alloys. Okay, thank you for watching. That's for today.